Our top story tonight, make the universe great again. You knew I couldn't get through this without one election pun in this, right? Okay, so what am I talking about? Well, let's start back in 2004 with the Hubble Ultra Deep Field. Now, this is a picture of lots and lots of galaxies. How many galaxies? Well, some of you may know, but actually we do a educational activity where middle schoolers count all the galaxies in the Hubble Ultra Deep Field. How do we do it? Well, we divide it into 100 smaller squares, okay? And then we have the middle schoolers look at these individual squares and then count the galaxies in them, okay? They usually come up with like 50 or 70 galaxies in these. And then if there are 100 squares and there's, say, 50 galaxies in each, how many are there total? 50 times 100, 5,000, okay? So they tend to get 5,000, 10,000 galaxies or so in this. And, well, 5,000 to 7,000 is what the middle schoolers usually estimate. When you do it really carefully by astronomers, they count about 10,000 galaxies in this image. Now, this is a really tiny image. So if there are 10,000 galaxies in this image, how many are there in the entire universe? Well, to do that, you then have to know how big this is on the sky. And so we walk the middle schoolers through that part as well, and we say that, okay, well, here is the size of that ultra deep field compared to the full moon, the size of the full moon on the sky. All right? And it's, you know, it's a small part of the full moon, and the full moon itself is also a small part of the sky. And if you do the mathematics, all right, the size of the Hubble Deep Field compared to an entire sphere, the number is, across the entire sky, there are 12,746,784 patches the same size as the Hubble Ultra Deep Field. Okay? So, 10,000 galaxies in the Hubble Ultra Deep Field, 12 million ultra deep fields across the sky. If it's representative, then we get about 120 billion galaxies across the entire sky. So, using that ultra deep field, which I said we observed over a decade ago, to the depth of the ultra deep field, there are roughly 100 billion galaxies in the universe, okay? And that has been sort of our standard number for the number of galaxies in the universe for over a decade. But what about the galaxies that Hubble doesn't see? Because notice, this says to the depth of the Hubble Ultra Deep Field. There are things that Hubble doesn't see, right? They could be too faint for Hubble to see them, or they could be too small for Hubble to see them, or they could radiate in infrared or other wavelengths that Hubble doesn't see, right? So, we recently had a paper called The Evolution of the Galaxy Number Density at Z less than 8 and Its Implications, which may not make much sense to you, but the idea is to try and account for all the galaxies that we don't see in the Hubble Ultra Deep Field. So, here is the study. And I'm going to read this verbatim because there's a lot to it, and I'll think. How many galaxies are potentially detectable within the universe if deep imaging over all wavelengths could be carried out in every location of the sky without any interference from the galaxy or other contamination? So that covers all the things that I just said. The entire sky in all wavelengths without any of this foreground contamination or stuff blocking, right? Which you could see every single galaxy out there. That's what this study is trying to do, okay? What is a galaxy for them? They say, well, they consider galaxies down to 1 million solar masses. Our Milky Way galaxy total mass is about 10 to the 12 solar masses, maybe 10 to the 11 solar masses in stars. They're considering things much, 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 much smaller, okay? Even the Large Magellanic Cloud is like 1 billion solar masses. So this is 1/1000th of even, you know, our satellite galaxies. So these are really down, they're trying to look at the very smallest type stuff for galaxies. And also, they're looking at the number per co-moving volume. I need to point this out because we're going to talk about number density. And we know the universe is expanding. And so as the universe gets bigger, of course, you have fewer galaxies per volume, right? No. Not in this. We're talking about what we call co-moving volume, so the expansion of the universe is already factored out, okay? So the densities are factored, the expansion of the universe has been factored out when we're talking about the densities here, okay? So this is one of the key figures in their paper, all right? And this on the y-axis is the number density of galaxies, all right? And on the x-axis is time in billions of years, all right? Starting at the Big Bang here up to almost the present day over here. And there's lots and lots of points because they're trying to normalize it to data that is observed. Galaxy surveys looking deeply at the various galaxies in the universe, counting up galaxies, and they're trying to normalize their theoretical prediction to that. And this solid line is their best fit to the model results. And you'll note that it's down around 0.1 for most of its length. And then in the first billion years of the universe, it jumps up by a factor of 10 or more. Okay, the number of galaxies per unit volume in the first billion years is much, much larger than what we see out here. And where are we going to see most of our galaxies with Hubble? Well, we're going to see them mostly out here. That first billion years of the universe is extremely difficult to look at. Okay? So they're saying that we're missing a lot of galaxies over here because the number density is so high and we're not seeing them. They say that there are more low-mass galaxies per massive galaxy at high redshifts than in the local universe by a large factor, a factor of 10 or so. And their result is the total number of galaxies in the universe is 2 trillion, almost a factor of 10 higher than would be seen in an all-sky survey at HUDF depth. So if we could do the Hubble ultra-deep field across the entire night sky, they're still saying we would only see 10% of the galaxies in the universe. Kind of impressive, huh? All right. I will caution, however, that it's a theoretical study. It's not an observational study. Nobody has actually seen these galaxies, okay? So what questions does it bring up in an astrophysicist's mind? First of all, are the extrapolations to low mass robust? We have some good observations that go down to 10 to the 7th solar masses, okay? And they sort of disagree with some of these predictions, but they sort of agree. You find really good agreement up to like 10 to the 10th solar masses. But when you start going below that, you start getting a little bit of disagreement. And here they're extrapolating down to 10 to the 6th solar masses. So I'm not quite sure, as I read the paper, is it really robust down to 10 to the 6th? It's a very good paper, okay? I'm not trying to knock it. I'm just trying to give you ideas of what an astronomer thinks when they see things like this. And then my second question would have been, will JWST be able to see these galaxies? As you know, we've got the James Webb Space Telescope launching in 2018. We're going to be the scientific home of it here. We want to know, hey, if there are if we're only seeing 10% of the galaxies in the universe, can JWST see those other 90%? The answer is, unfortunately, not. We're talking 10 to the 6th solar masses. We're just getting too small for JWST to see, okay? So we won't be able to verify this result with James Webb, okay? Which is, of course, one of the things that we would love to be able to do around here. But if this is true, all right, if this prediction is true, we'll figure out some way to figure out how to constrain it with the James Webb Space Telescope, or maybe even with later Hubble observations. And then finally, it brings up a question that's sort of a classic in my mind. What really qualifies as a galaxy, okay? Because we start talking about the early universe, and we're talking about the building blocks that will come together to form what we considered a real galaxy. Like this is a real galaxy, okay? It's a nice, big, large galaxy, all right? But if you take something that is 1/100,000th the size of this, okay, does that get to count as a full galaxy? All right, so when we're talking about these numbers of 100 billion versus 2 trillion galaxies, we're talking about the evolution of galaxies over time, the development of them from these small things to these big things, the mergers. You may have a trillion galaxies early on simply because so many of them merge together to form a much smaller number later on, right? So you're getting into not just galaxies across space, but galaxies across time. It's a time-warped view of the universe that you have to think about. And do these small little objects, there aren't what we would normally consider galaxies in the local universe. How much does it count? And so you get some very interesting questions. So this was a major press release for us this month, got a lot of attention, and I think it brings up some really great questions as to where we will want to look in cosmology for these very earliest galaxies in the universe. And it brings up an amazing prospect that, hey, 90% of the galaxies out there still have yet to be discovered, which is always fun as an astronomer. All right, our second story tonight, the ghost of a star. We had a Halloween release last week, and I couldn't be happy with just this. I also called it a beautiful nebula. So we released this image on Thursday. Ooh, spooky. Let me tell you the story behind this image, okay? It's a single filter image that was colored green. Actually, it's a broadband image, waveband, so it does actually have a green tinge to it. But let me explain a little bit more about it, okay? So the story starts a little while ago, on July 4th, 1054. As you can read here, if you read ancient Chinese, the Chinese astronomers on July 4th, 1054, saw a guest star appear in the sky. I don't read Chinese, so this could be a recipe for mushu pork as far as I know, but I can look at the hieroglyphs in Shako Canyon, and here is the here's the crescent moon, and here is the guest star depicted there, about a hand's length away from the crescent moon on the sky, which also is believed to depict this guest star appearing in the sky 1,000 years ago. All right. If it was in the constellation Taurus, and when we look at the constellation Taurus today, we see that. The Crab Nebula, okay? What this was a supernova explosion. The explosion of a star becoming so bright that it could be seen during the daytime here on Earth, all right? And this star, the guts of it has blown across space at 10 million miles an hour for 1,000 years and created this gorgeous nebula. Now, this nebula is shown in 3 filters, hydrogen, nitrogen, and the broadband, a little bit of the broadband one that I talked. I think maybe it's hydrogen, nitrogen, oxygen, and a little bit of the broadband. And you can see all this filamentary stuff out here. Well, that's the narrowband filters that just pull out the individual elements. Okay? The ghost image that I showed you before, when I overlay it on top, is there. All right? So I'm going to blink back and forth. So here's the normal crab that we're used to, and there's the ghost. Normal, ghost. Normal. You can look right in here. You can see that stuff. That's not filled in the ghost. All right? So what we're seeing here with this this broadband image is that it is filling in much the sort of egg shape of all this filamentary structure sort of creates an egg shape, and the interior is filled in with this ghost image. All right? So here are the 2 images on the same scale, just separated so you can take a look at them. And you can see this blue image here roughly corresponds to the green that we released in the image on Friday. But there's even more cool stuff in this image. If we look straight in here in the interior, you can see there's something funky going on in there. Well, Hubble released an image of that previously. This is the central region. You see sort of ring structure here. Well, that comes out beautifully when you look in X-rays with the Chandra X-ray telescope. All right, you have a beautiful ring structure here, you have a bright dot in the center, and you have this material being spewed off. This is the dead star. This is the stellar remnant. It is a neutron star, a ball of neutrons about the size of the Baltimore Beltway, okay? Just all packed in, spinning 30 times a second. We know it's spinning 30 times a second because that neutron star has an immense magnetic field, all right, that creates pulses when that magnetic field sweeps across our line of view. 30 times a second, we get pulses from this, and hence we call it a pulsar. So the pulsar at the center of the Crab Nebula has this amazing magnetic field that's sweeping around 30 times a second, which of course is creating tremendous amounts of energy. So if you look at that in polarized light, and you're going to learn a lot about polarized light tonight, right, Toby? Yes. If you look at it in polarized light, you can actually see some of the pulsation, some of the effects of the magnetic field. This is a time-lapse series, okay? All right, and you can see material flowing away from that central neutron star. And it is a broadband image plus some polarized light in order to see the material flowing away, all right? And so in the Halloween spirit, since we're Baltimore and Edgar Allan Poe is related here, we call this the telltale heart, or the beating heart of the ghost of the Crab Nebula. So even though it's a dead star, it still has a beating heart. And that was our Halloween release for this year.